Today we are going to see a very old and popular probability problem. It's known as Buffon's needle problem. It originated in 18th century, and the person who was responsible for this problem was known as Count Buffon. He was a French count. Probably he was in the same situation like us at that point of time. Counts did not have much work, so they were solving mathematical problems. We are also stuck because of lockdown. So we will try to solve this problem. Suppose you are given a plane, parallel lines drawn at a distance of 1 unit, let's say 1 meter. For the sake of keeping things simple, let's assume that this is an infinite plane. So you have an infinite plane and parallel lines are drawn 1 meter away horizontally on this plane. This is the setting, and then you drop a needle now of unit length. Okay, so this is a needle and the length at this point, let's start with 1 meter. Okay, this is the same as the distance between parallel lines. So we drop a needle on this plane, and the question is, what is the expected number of intersections? A nice idea would be to pause the video, you trying to see whether you can figure out the solution. As a hint, it's an integration problem, so you can do it. Let me show you the solution now. So we can assume that the needle, or I would say the midpoint of the needle, is close to one of the lines. So let's say it is closest to this particular line. And to define the sample space, I will say that since the distance is 1 meter, so I will say that the needle, the midpoint of the needle, should be at most ½ meter away from some line. So let's say this is the line. So the distance of the midpoint from the line is at most ½ meter, and the other parameter is the angle. So let's say it makes an angle of theta. So here this was our needle. So we have divided the sample space into two parameters. One is the distance of the midpoint, and other is the angle from the vertical. In this case, you can think of it as the sample space to be a rectangle, where this is theta, this is the distance, call it y. So the distance goes from 0 to half. Angle, you can say, goes from -π/2 to π/2. So there is a total distance of pi in the angle which we want to worry about. So my needle can lie at any point in this rectangle. So first task would be to define the probability density function for such an experiment. Since we were dropping the needle uniformly, we would assume that we pick a point uniformly at this rectangle. So the area of the rectangle is half times pi. So our probability distribution should be 2/pi. Here y varies between 0 and half. Boundaries are not important in the sense that I can take it to be strict inequality here. It doesn't matter. And theta varies between -π/2 and π/2. So this probability density function picks a point uniformly from this rectangle. As an exercise, you can check that this is a PDF. So if you integrate this over this interval, you will get 1. Now we have to calculate the expectation. So let's say y counts the number of intersections. Expected value of y integral from 0 to half minus pi by 2 to pi by 2 fy theta dy d theta. I'm missing just one term, which is the number of intersections. So I will just call it iy theta. So iy theta is the number of intersections when the needle is at distance y and a simple geometry will show you that the intersection iy theta will be 1 if my L is less than half cos theta. Iy theta is 0 if L is, this is not L, this is Y. Y is greater than half cos theta. Okay, there is a boundary case, which is that when Y is equal to half and theta is equal to 0, in this case I will have two intersections. But remember that the boundary case is not very important for us. That will contribute 0 in this integration, so we will not worry about it. So using this, expectation of y is minus pi by 2 to pi by 2, 0 to half cos theta dy d theta. It's a simple exercise to calculate this integration, and you will get it to be equal to 2 pi pi. This was not very difficult. It was just a double integration. We had to make sure what was the sample space. Once we realized that the sample space was just a rectangle and we could define our iy theta, a simple integration gives us the value. But the problem is not so simple. Let's increase the stakes. The needle, let's say, can have arbitrary length. Not just that, it could be of any shape. It could be W, needle could be of this shape, needle could be of this shape, whatever way possible. So I will tell you the shape and I will tell you the length of the needle. Can you again find the number of intersections? The correct question to ask is expected number of intersections. And you already see, probably pick the needle to be W, and you will see that it is very, very hard to now decide the sample space as well as decide this iy theta. So let's solve this question in a very, very different way, and you will see that the answer will just pop out. Again, let's say y be the number of intersections. Divide the needle into small parts. Say xi is the number of intersections of ith part. So I have divided my needle into very, very small parts, and the number of intersections of the ith part I am denoting it by xi. So say I goes from 1 to n, and y is the total number of intersections of the needle. Pay close attention to this. Now, clearly as a random variable, y is equal to x1 plus x2 plus xn. In any experiment, the number of intersections of y is equal to sum of the number of intersections of the first part, second part, third part, and so on. So this is pretty clear, but by linearity of expectation, and that's the magic word here. This entire exercise is done to show you the power of linearity of expectation. So this follows from linearity of expectation. once you realize this, now as n tends to infinity, the parts become smaller and smaller. And they look like a small line. And whatever be the shape, we can assume that the number of intersections are same for that small part. In other words, expectation of y should just be proportional to the length of the needle. Right? So this is the important part. I will once again repeat it. So we know this. Now when n tends to infinity, the parts become smaller. So the expectation of y just looks like total number of parts multiplied by some constant. And the total number of parts depend upon the length. So that will directly give me E of y is proportional to the length of needle. So putting it mathematically, where L is the length of the needle and C is some absolute constant. I would like to emphasize what we have got here. This tells you the expectation in terms of the length of the needle. So most important, it tells you that number of intersections do not depend upon shape. This should come as a surprise to you. When we talked about needle of shape W, needle of shape Z or circular, it seemed a very, very difficult problem. Linearity of expectation implies that we don't have to worry about this. It only depends on the length of the needle. The statement of linearity of expectation is pretty simple, and you might have thought of it as a very intuitive thing. But this shows the real power. If in the beginning of the problem I had told you this statement that the expected number of intersections do not depend on the shape, it would have been hard to believe. But this statement comes almost directly from linearity of expectation. This is the power of linearity of expectation. Again, the important point was clearly the random variables x1 to xn are dependent. It's not that they are independent, but for applying linearity of expectation, it doesn't matter. We can even apply linearity of expectation for dependent random variables. This is always true. And so we get this theorem. The last thing to check is the constancy. How do you find constancy? And for that, we just need an example of a needle and number of intersections. Since C is an absolute constant, even if for one case we know the expected number of intersections, we can find C. And yes, we know for the needle, straight needle of unit length, we know that 2 by pi is the number of intersections C times 1. This implies C is equal to 2 by pi. But actually, there was a case where you even didn't have to do a single integration. You didn't even have to find the number of intersections for the straight line. Again, pause the video and think about a case where you definitely know the expected number of intersections. The answer is a circular needle of diameter 1. If I throw a circular needle of diameter 1 on these parallel lines, the expected number of intersections will definitely be equal to 2. Because however you throw the needle, the number of intersections are always 2. Now the length of this needle is just pi. This will also give you C is equal to 2 pi pi. So we get the theorem that for any needle, the expected number of intersections are 2 by pi multiplied by This solves the Buffon's linear problem. And the thing to notice here was the power of linearity of expectation. I will finish the lecture today. From next week, we will start seeing the concept of independence. You have already have a notion of when random variables are independent, dependent, when the events are dependent or independent. Thank you.